computer science has come to as we know today. Do I need to mute someone? Okay, great. So as we go forward, let me disable the settings of externals. When you join through external thing, it's very annoying. It disturbs the class. So I'm requesting others who are not joining from their official email ID to start joining in the meeting with official email IDs. All right. So as we are going to build our understanding of foundation for computer science, it's important to go through the entire chronology of how computer science has come to be as we know today. And through a series of, I think, 2 or 2.5 lectures, we will try to discuss and understand from where computer science has come up to what it is today. And, not only from a knowledge point of view, that, while it may be admirable to know how the developments have took place, it is more important to understand why they took place and why the people who were involved in it, sort of started tackling such kind of problems, and what was the thought process behind it. Because evolution always goes on. By the time you graduate, there would be some different developments in the domain of computer science. So that is why it is important to get a taste of where we have come from in terms of computer science. So as you can see, that the topic of the lecture is history of computer science. Why do you think knowing history is important? What is the importance of knowing history of computer science or history in general?
We can know the mistakes and we can learn from them.
Okay,
History might repeat itself in future.
1% at a time, yeah.
History might repeat itself in future.
Okay, so the very fact that it might repeat itself, how does it help you?
Ma'am, we can take an idea how far we stand from the history and how developed we are.
Yeah, it tells us how far we have come up, how we have.
How
Ma'am,
and
to
why
assess,
we
to
how
assess and analyze patterns from history and to see what like future predictions.
Okay, so to take lessons from our history. Harsh, you were saying something?
and
It,
how
it
and
will
why we are get here and why we are studying this.
Okay,
it will allow us to do better designing of like programs and computers.
okay. Learning from our history and all our mistakes and the good things also. History is not only about learning from mistakes, but also what worked and what did not work. From
we
learning.
can understand the we can understand the value of the topic.
Okay, so can you elaborate a bit?
When basically we can understand how the topic developed and what is the means uh, the value
Okay.
of the
So,
topic.
okay, so you use the word develop. So why is it important to know how a particular stream has developed over the period of time? What is the
Uh,
purpose it serves?
it might develop in a similar way in the future also, so we can understand it and link it with the past.
Ma'am, such that no mistake can be repeated same.
Okay,
Ma'am, we
yeah.
can relate the present day growth to the history, to the time when it started, and we can link it with how it has been grown right now.
That's a very beautiful point. So why do you think, Sashank, that knowledge of how to relate our current and past, why it is important?
Ma'am, it is important because the way it has been developed, the innovation which has been took place. That's why. So,
So how does
Ma'am,
this
ma'am,
help
we
us?
can get an idea what development can be made in the future at
Okay,
the current rate or at an exponential rate.
yes. Sai Krishna, you want to say something?
It helps us to decide and improve upon the existing system. Like, for
Okay,
example, before digital computers, there were analog computers, and after investing a lot of them in the world wars, they decided that analog computers were not developing to the current needs. So then they started the digital computers. So like we can identify needs, and with those needs we can invent new technologies by learning history.
Okay, yeah. I mean, that's a very good gist into the history of computer science, Sai Krishna. Thank you so much. Anyone else? What do the girls think? Why is the study of history important? I see that there are 16 girls in the class from the survey that you have signed up in the handshaking. Any hints over there? Okay, so as most of you have mentioned, history helps us to study change. To study history is basically to understand how the changes and developments and evolution in a particular field have happened. It not only tells us how far we have come, but it also tells us that all of us stand on the shoulder of giants. The computers that we see today, obviously they have had a journey, and that also tells us about the responsibility that we have when it comes to technology, and the role that we will be playing in something that will be developing after 50-60 years, or even after when we are no more over here. So that is why studying history helps us to study change and past. As you have most of you have mentioned, it teaches us about the present, and studying history provides a perspective on things and contributions of past explorers, on whose contributions we take the exploration forward. So it sort of forms a base, a springboard, if you will, and then it helps us to launch our own ideas and think and try to understand the present from the past, and also to understand the potential that lies in the present going forward. So that is about the history in general. Now, but why should we study about the history of computing or computer science or computers? What is so fascinating about the history of computing? What can we hope to learn when we study about history of computing or computational sciences?
A great leap that we have taken before computers were developed.
Okay, yeah. Sai Krishna, go on.
Computers helped evolve human society. So along with the computational work we do, for now, like nowadays, even the social medias and all, like the access to that dictates how we behave in society and all.
Okay, so yes, evolution of computer science did impact how our societies developed or evolved over a period of time. So that helps to understand how the entire ecosystem works. What else? So when you think about the power of computation now and you compare it to maybe 200 years back, what do you hope to see in the history of computing or computer science?
Computers have now become an epitome to technology. So computers are directly related to technology, and we hope that we will be getting better technology by developing better computers in the future.
Okay. Yes.
Much more compacted and portable computers, and ma'am, there are several more features than there were during the old times. Like ma'am, initially when the computer was made, their aim was to like just for calculations, but
Yeah.
today we have so many, we can use them for several purposes.
Absolutely. Absolutely. Did you?
Ma'am,
Yeah. Sankalp.
ma'am, it can help us to predict the future of computer science as well, like how much it has evolved from the past to now, so we can predict how it will evolve in the future.
So studying of history tells us about the potential that lies in the future. Yes, go on.
Like ma'am, if like in the past we had the computers that takes input, then they gave output. Then we came to an idea where we were like ones and zeros. And finally, like currently we are researching on ideas if we can have more than ones and zeros, and that's those new computers, quantum computers.
Quantum computing. Yes.
Yeah.
Yes.
So that in that sense, we can have a separate perspective if we study our history. And like, for example, if we have ones and zeros, then why not other than ones and zeros, and have a separate perspective?
Yeah. Why only binary? Why not trinary or quaternary? Yeah.
Yeah.
Good perspective. Pushkraj is saying to take brief overview of development in the field. Yeah. So when we see as we will be seeing throughout the starting from 80s and much before, how computing has evolved, and basically computing was happening even before computers, right? Mathematics was already there. What was the need that computers as a devices had to be formed?
ma'am, to help humans reduce the labor for
Ma'am, computers
solving
have
complex
an efficiency much higher than humans.
Okay. Yeah.
Much
Cycle.
Ma'am, to solve a complex maths problem, like which is impossible for humans.
Absolutely. So yeah,
much faster and much accurate.
faster and
To
accurate
reduce man labor.
to reduce
To
man
reduce
labor.
my-
Sai Krishna, you want to say something?
Yeah, so as everyone said, they help reduce our time and made our calculations more efficient. Like there were computers in the olden days which helped us to calculate and track the motion of planets in their orbits, and it also helped us track the eclipses, which allowed them to maybe participate in festivals or whatever.
Right.
Ma'am,
Right.
and accuracy because computers are less likely to make mistakes as compared to humans.
And storage as well also, ma'am, because storage computer is far more ahead than human brains. It can store much more than what we can do.
The processing power of computers beats the
Yes,
human.
yes.
Yeah. So people on chat also are mentioning to understand the thinking process and to evolve to make the human work easy by solving and to eliminate more cases in efficient time. Yeah. So most of you have got it right. So we're sort of bothering with this history of computing or computer science. Most of the time, these terms are used interchangeably to develop a better understanding of the world of computing. To understand that not only how technology has evolved, but how it actually impacted, the different areas of our world. It impacted our society, it impacted our government, it impacted the way the world wars were fought. As we will see that digital computers actually started because of the need to understand some coded messages in the Second World War. That was the trigger point why the shift from analog to digital had happened. So moreover, studying history, and personally I have never liked history when I was in school, but when you are very invested in a particular field, and out of your interest and curiosity, then you want to know, okay, how it has evolved to the current place. And there's a way of exploring history. History is definitely fascinating, but the way we explore it and the way maybe our instructor also teaches us matters a lot when it comes to development of interest or not. So similarly, when it comes to history of computing and computer science, it will help us to understand, okay, this particular device on which we are today having our virtual class in this COVID-19 pandemic, there's a history before it. And as much as it, surprises us and amazes us, it also makes us very grateful. Because of these technologies, we are able to, go on despite the difficult circumstances. And this is how, history teaches us about developments that have happened and also assures us the development that will continue. And with that base, we try to understand, the history of computing. So calculation was happening even before the computers was invented. The tribal areas, the tribal people, they used to have some recurrent functions, or some used to observe some religious festivals and ceremonies. So they needed something, some logic to count the days, the months, and the seasons. So counting was already happening, and computers, as we know, mostly make our computations faster. But these times, today's computers work not only on numbers but also in images, videos, sounds, music, and whatever. So the data that is fed to today's computers is not only numerical, but it's of various different forms. So how many of you know about this? How many of you have worked on something which is seen like this? What is it called?
Abacus.
Abacus.
So how many of you have had the opportunity to play with it in your schools? Raise your hand. Okay. So one of you, will you tell me what exactly were the things that you were doing with Abacus? In which class exactly?
Ma'am, I have studied
Second.
I'm first.
Seventh.
Fourth.
So what kind of operation, what kind of things you were doing with Abacus? Can you remember?
Mathematical operations.
We were taught some
Subtraction.
tables, and according to that, we did calculations.
What sort of calculations?
I'm like
Ma'am,
Number to huge number of huge amount of like large numbers, and then like
complex sums.
Yes, ma'am.
Speed
Within our fingertips.
calculation. It was all
Speed
about doing
calculation.
faster calculations. Like if we wanted to add 2037, like
Okay.
4-digit, 5-digit, 6-digit numbers, then it was very fast with that.
Okay.
So
Student?
for the process, we were taught some tables and formulas which we have to keep in our mind, and then with the help of those, we did the calculations.
Okay. Okay. So you understood the calculations. Yes, Rajat. Athar, if you want to say something. People who are raising hands, you can say one by one.
Ma'am, like we were taught to do fast calculation. Like a normal being will take pen and paper. He will do it in paper. But we are taught in such a fast way. You can tell in within seconds.
Okay. So why is it that the abacus are fast according to you?
Ma'am, it visualizes the process.
Yeah. Yeah. Human mind is wired for visualization and understanding things by visualization. Yes, Advait?
Excuse me, ma'am.
Ma'am, the thing is, we would be able to do them faster because we took a parallel approach. Like we didn't do it in the conventional, like methods we are taught in school, like the subtraction, multiplications, and also we were able to do tables up to 1,000, like 3x3 tables, like very fast because we were able to picture them with our like mentally imagine them. We didn't need a physical abacus as well.
Okay. So I remember in my school, I think that they taught us what is ones, tens, and hundred place and thousands place maybe using abacus. So you know that decimal system, how 120 actually is 123. So that I mean personally, that's all I remember when it comes to abacus class.
Ma'am.
Yeah.
How this works, ma'am? I have never used, ma'am, it.
Okay. So who is gonna explain to your friend Apoor?
Ma'am, can I go ahead?
Yeah, go ahead.
So the beads, like, so thing is like there is one central axis which is like the ones place. So if you can see, there's like a distinction on the top. So like the abacus we had, it only had like one bead on top. That was like to represent 5. So it's like you have 4 digits in the bottom, like the lower area. Those represent the 4, like 1, 2, 3, 4, and then you add 5. So you have the ones place, you have the tens place, like you go on up until like millions, and on the right hand side of the ones is like you have the decimal system as well, so like 0.1, 0.01, so on and so forth, and using those you can do mathematical tasks like you have 4 basic operations, and you can also do powers and all of that.
Yes. Thank you, Advait. Apoor, I also encourage you to see a YouTube video on abacus, a very simple one. Okay.
Okay, ma'am.
I understand that few of the students may not have come across it. So an abacus is actually available on Amazon also. So just see a video on YouTube and try to see how it works. So these are our earliest ideas of computing. Amog, you want to say something? I see your raised hand.
No, ma'am, I had previously raised the hand for the abacus.
Okay, okay. So okay, all right. So before 1900s, abacus were generally prominent, and these also emerged from the human need to count. Much later, the binary system was developed, and in our future lectures we will talk about binary lectures and why only binary system was developed, why not other kind of systems were explored. So coming from abacus, that was the first automatic computer. It was the most common, which comes from China, and it was man's first attempt of automating the counting process. Now, we were counting before also, but the need for a device, an electronic or mechanical or an automatic device that could do large number of computations fastly was realized very quickly. And is there any analogy you see between today's world? So what is happening in today's world at the very fast pace, and the methods are being developed for that? If I ask you to see an analogy, so during that time computations were happening, large scale computations were happening, so computers were sort of invented and envisaged. If I bring you back to today's world, is there any analogy you can see? What is it that is taking our world by the surge in today's world? Aditya.
Ma'am, the number of skills required to perform basic tasks have reduced.
Okay, okay. Due to computers, okay. So if I ask you, you see data science, data analysis going everywhere, okay. Why has suddenly data science and data analysis, business analytics become such hot fields in our world? Yes, Advait.
Ma'am, to give users a personalized experience.
But that was happening before also. Why we have become so fascinated and obsessed about developing methods that can do number crunching as fast as possible? What is the driving factor after that?
Ma'am, the data has increased.
Absolutely.
So to
Yeah.
manage that, we are needing data science.
Absolutely. So data science, data computation, statistics analysis was happening before also, but because of the rate at which the data are increasing, data are plural, the data are increasing. That is why we have been pushed, to expand our horizons to things like TensorFlow and highly sophisticated machine learning algorithms. So just wanted to draw an analogy between computation was happening even then, but the scale at which it was happening, the demand at which the computations were required, led people to start thinking in the direction of, okay, now human labor is not enough, we need some machine to do that. In fact, you will be surprised to know what was the old meaning of computer.
Common operating machine, generally used for programming, education and research purposes.
Okay, so even before computers were considered to be that, what was the meaning of computer?
Performing mathematical.
So you would be surprised to know computers actually meant people who were doing the computations manually. So in previous times, computers actually meant the people or the personnel who were doing the computations. Much later, it came to be known as a particular device that would do the same. So I will just show you a small video on the history of computer science, and it's actually a 7-minute video of a BBC documentary. So there's it's a playlist of BBC documentary. I encourage you to watch it fully. So I'll just show you a glimpse of it. So what are you seeing on the screen right now?
PPT.
Okay. What do you see now?
Yes, ma'am. Now it's visible.
Some video is visible.
Okay, so this is a history of computers. This is just part one of the BBC documentary, and there are around, I think, 10 parts. I strongly encourage all of you to watch it, to understand. All right, so let's see.
Programs for the Cambridge machine not using a simple code.
Is the voice okay? Are you able to hear the voice of the video?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Let's watch it then.
Programs for the Cambridge machine were written out using a simple code. They were converted to punched tape and then fed into the machine. Scientists from many disciplines soon learned how to prepare programs. These massive number crunchers were so fast that one such machine could do the work of 10,000 human computers with calculators.
Ma'am, the audio is gone.
Ma'am, the audio is gone.
Became familiar with the machine, they discovered that it opened new possibilities. The availability of computers was essential to the development of new sciences, like radio astronomy, which generated masses of data. And in many other branches of science, now huge calculations could be done at speed, the impossible became possible. Soon it was realized there would never be enough computing capacity.
The scientists were interested in the computer mainly as a tool to widen their horizons. But newspaper headline writers wanted to believe there was more to these machines than that. And they had good authority. Alan Turing, a brilliant mathematician, always saw computers as much more than mere number crunchers. The vision Turing had of computers even led him to design one. Pilot Ace, the only more or less complete machine that survives from that era, was based on that design. But Turing hoped to use it for more interesting things than arithmetic.
Long time ago. But this was where computers started, electronic computers started. This is one of the first stored program computers. It was designed by a man called Alan Turing, who was in fact a British mathematician who was involved in cracking codes. in the war, in the Second World War, cracking the German codes. Yes? The war.
Turing's ideas on computers went back even further than the war. In 1936, he had published a paper on an abstruse mathematical problem. In that paper, written a full decade before computers were built, he wrote about computing machines and demonstrated theoretically that one such machine could, in principle, do any logical task a human could do. Turing realized there was nothing special about computing numbers. It was just one step-by-step logical process which manipulated symbols according to certain rules. But there were others. Code breaking, for example. It took symbols, usually letters, and transformed them to unscramble a message. If manipulation of numbers could be mechanized or done by a machine, then, said Turing, so could manipulation of letters. When war broke out, he had a chance to test his ideas. But the work done at Bletchley Park by Turing and the other code breakers was so secret that its existence would not be revealed until the 1970s. The encoding methods used by the Germans in the Second World War relied on machines. Enigma, the best known, encoded the day-to-day traffic of the forces. This was Turing's main area of responsibility. But the most secret of all the messages, including some from Hitler himself, were sent from teleprinters attached to another machine. Called the Lorentz, it had shifting wheels which scrambled the letters in a pattern that was continually changing. Alan Turing worked out one of the logical strategies the code breakers used to attack it. But the task was hopeless. It was much too slow to be useful. The only possibility was to build the rules of their strategy into a machine. Colossus, an extraordinary construction, was a partial embodiment of the computing machine Turing had imagined. It was electronic and therefore very fast, and it computed not numbers but code letters. Colossus began operating in 1943, the same year as work on ENIAC began. But whereas the ENIAC's vacuum tubes did arithmetic, Colossus's circuits carried out the logical steps of a code breaker. Colossus broke so many top-secret messages that, unlike ENIAC, it undoubtedly did help to win the war. It had a less obvious impact than ENIAC on the development of the computer, but it confirmed what Turing had always believed, that a computer was not simply an arithmetic machine. Because of the secrecy surrounding Colossus, Alan Turing's remarkable insight into what a computer could be has only recently been recognized.
Turing had this extraordinary, almost unique obsession with looking at a problem as though it was the first time that anybody in the world had ever looked at that problem and taking it completely fresh. There was a small group of us who came very much under his spell in terms of the vision that he had for what would be possible after the war, to develop computing machines, which in itself was an amazing idea, but not just for numerical calculations, but for symbolic, non-numerical calculations, which could simulate the processes of logical human thought, and above all, of machine learning.
But unfortunately for Turing, the response of young colleagues like Donald Mickey was not shared by the establishment. Having devoted great effort to designing his ace, he realized it would never be used as he had hoped. He wanted to simulate human thought, but the machine was destined to spend all its time performing scientific calculations. When it became entangled in bureaucracy, he left in disgust. Moving to Manchester University, he had a chance to try out a few of his ideas for non-mathematical projects. In 1954, this remarkable genius committed suicide following a prosecution for homosexuality. So he never saw which of his dreams came true.
He never lived to see that Eckert and Macauley's far-fetched scheme to start a computer business would end up launching an industry. He never saw how engineers were able to shrink the main circuitry of a computer and put it onto a single chip that you could fit on your hand. He never saw that one day computers would play chess better than all but the very best human players. Today, computers are, as Turing foresaw, universal machines. Their uses are limited only by our imaginations.
What is that? No?
Today, children look back at the machines of Turing's time in astonishment. Computers are such common objects, used for so many things, that it's hard for them to understand that once all people did with them was compute.
So you can watch it later. I will share it. So what are your observations from the video? What are your observations from the video? What is it you observe?
When people regarded it only as an arithmetic machine, as a calculator.
Okay, so note the important ones. The mathematician started the computer revolution. What does it have to say? And what are the sizes of computers that are seen in the video?
Size
They
of
were
the
Huge. Very large size.
Entire rooms.
Very huge.
Very huge, almost the size of the room.
Consume a full room.
Yeah. So the thing is that now when even a smartphone that you use in your hand is a sort of computer. Okay, but why do you think the size has decreased over the period of time for computers?
Because old computers were bulky and were not portable, not easy to use. But today we have computers which are very compact, and they can be multitasking for us.
Okay.
They used vacuum tubes which were very large and bulky,
So
and we used
because of transistors.
Size
of the semiconductors.
Chips, transistors, semiconductors, absolutely. Microprocessors. Basically, with the evolution in the microprocessors and the number of computations that can happen on a single, place of the chip. Because of that, our processing power has improved, and that is why the size has shrunk a bit much. Sai Krishna, go on.
There was also the possibility that small insects could get into those large machines and interfere with. I think that's where the term bug came from.
Absolutely. So in Mark 1 computer, actually when you study about software engineering and you learn about debugging, that's the history of how debugging got its name. Yeah, it was actually a hardware bug. Sai Krishna, that was found. Thank you for mentioning that. So I will share the video, and I think one of our friends has also mentioned a movie called Imitation Game, which showcases Alan Turing and how he makes Enigma during the war. So Amok, it would be nice if you can also share the links to watch it. I would also try to watch it. Thank you for sharing that with us. So moving on, gradually the development of binary logic started, and it was invented by late mathematician, in the 3rd century BC. And in this system, any number can be represented with just zeros and ones. So how many of you are familiar with binary representation of numbers?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Yes, ma'am.
So anyway, for those of you who have not had an introductory course on computer science, we will be covering up that also.
Yes, ma'am.
So before 1900s, there are two prominent names that come up, which is Charles Babbage and Ada Lovelace. So Charles Babbage, he was working on two mechanical devices. Now note the word mechanical. He was trying to do a lot more computations in an efficient way, and during that time he designed two things: the difference engine and the analytical engine. So basically the task of Harsh, you want to say something?
No,
So
ma'am.
so basically the task of these two engines was to automate and make the computations faster. And see, that remembering the names is not important, but what I'm attempting to do when I put these names and what they have done is that almost they were working on the problems. And why do you think, what would have motivated these people to actually go on and find the solution, to develop things like difference engine or analytical engines, or machines that can have sufficient power to solve a complicated problem faster? It's how you think about it. So this one person, Herman, in the last one, it is mentioned that he invented the modern punched card for use in the machine he designed to help tabulate. So in census, especially in US census, when people are being counted, and every regular period of time it happens. So that was the acute problem that was faced of counting at such a large scale. And it was during that time that something called a punched card was used to understand, the total tally of the census. So these were the things that were happening, before 1900, which is more than 100 years from today. Sorish, go on.
Ma'am, why you emphasized on mechanical devices?
Okay, so previously when a system needed to have an input and output, the input had to be fed in a very mechanical manner, like shifting of the shafts and actually manually handling the gears and things like that, so that proper sequence of events can happen, so till the input can go on to the output. But now it is automated. So, and that is why I emphasize on the word mechanical, because even though they were doing faster communication, but to operate it, a person was required to mechanically operate them. Is it clear now?
Yes, ma'am.
Okay. Moving on, so let's talk a bit about difference engine. And you don't have to remember the theory, but just how Charles Babbage was thinking late in the 1800s when he designed a difference engine. So basically his attempt was to to do the computations in less amount of time, and he theorized that it must be possible to design a calculating machine which could do these operations automatically. Now again, they were not doing anything different. They were doing the computations, but the sheer scale at which they were doing the computations pushed them to invent a difference engine or an analytical engine, if you will. So you see, even in today's world, when it comes to, we might be doing the same operation, but the sheer scale at which happens. Think about the evolution of cloud spaces. Why do you think cloud spaces have become very prominent storage services these days? Any reasons you can think of?
Very easy to access. We
Okay.
can access from anywhere in the world.
Okay.
It's free also.
It's cost.
You
don't have to carry hard drives and
amount of data can be backed up and can be retrieved later.
Yeah. So you see, as one of our friends had mentioned in the chat, that necessity is the mother of invention, and that has always driven the developments, and that will always drive the developments in time to come. So Charles Babbage was working on difference engine. He had a vision in his mind. He wanted to develop something that could do computations much more fastly. But in the mid, he had to, he dropped that idea and started working on analytical engine, which he thought it was a better idea because it was, really parallel to the decimal computer, which could operate on words around 50 decimals. So you see, it was a very amorphous thing from nowhere, from abacus, from counting on fingers, we came to abacus. From abacus, we have come to things like difference engine, analytical engine, and then we will be going on to computers that are size of the room, and then gradually in the 1970s we have something called as the home computers, and also supercomputers, and now we are in the age of development of quantum computers. So moving forward, Charles Babbage and Ada Lovelace are together often remembered as the founders of modern computing. However, Alan Turing is called as the father of computer science because it's, as we will see in our future lectures, that a Turing machine actually is what a computer exactly does. It follows a set of instructions, processes them, and gives some output. And Turing, I think in the 1936, he proposed this idea. The analytical engine is a key step in the formation of modern computer, which was proposed by Charles Babbage again. But the machine was never really built, and it is a mechanical general purpose computer that would run off a steam engine. Now imagine a computer running over a steam engine. What does this tell you? Why do you think a steam engine would have been required?
Ma'am, to provide the necessary power.
Okay, yeah. And today's computer, how do they derive their power?
From electricity.
Yes.
Okay. And what do you think is the reason behind the fact that the mechanical general purpose computers? Why do you think that would have happened? What is the shift from mechanical? What is the mechanical analog of the previous computers in our modern computers? What is the
Ma'am,
mechanical?
they had too much instruments involved, so they needed more power to run. So basically, a steam engine was required. But now the things are more compact, so we need less power to run do the same task. Actually, more of it.
Okay, so as the power of the processors have increased, the sizes have decreased. There's something called as Moore's law. Has anyone come across Moore's law?
Yes, ma'am. Yes, ma'am.
So what is that, Priyanshu?
After every
Ma'am,
2 years, the number
yes,
of elements on the integrated chips is halved.
Okay. For Priyanshu and Saikrishna, you want to add something to what Kalash said?
no, ma'am. The size of the transistors are decreasing at half. Are decreasing, ma'am. They are becoming half of the previous year, like something like that.
So, okay, so why are they decreasing? What is leading to that decrease? What is exactly happening? Size is half, transistors are doubled every 2 years, but what is the reason behind it?
Advancement in technology.
Technology, exactly. So there is nothing that is happening on the transistors themselves, but it just means that our technology is evolving at such a fast pace that the number of operations that it could do can do better in our modern times. So this is a description of a general plan of Mr. Babbage's calculating engine. You can see, I mean, the diagram is not very visible. This is the best out I could find from the archive of Charles Babbage. So as you can see, there is a lot of gears involved. There are mills for calculating, then storage of instructions, and operator for carrying out instructions, and reading and writing. So it looks very complex. It's hardly visible. It's complex. And today, when you open your laptops, how many of you have sort of done a post-mortem of your PC, your system unit, or your laptop? Prakhar, tell us about it. Arvind, Siddharth, yeah.
Yeah,
So,
ma'am. So nowadays there are no gears inside computers, and there are many electrical components. Hard disk is there, their RAM is there. We can change Wi-Fi card is there, but there is the main CPU that we are generally allowed to not touch and disturb.
okay, right. So if any one of you ever gets a chance, just try to open up your laptop. I'll be having a lecture on that also going forward. Like what lies in the inside of the computer. Would have shown it to you physically if you were in the offline mode. But it helps us to obtain a taste of, it almost sounds like magical that such massive machines of the size of, a particular room have now been reduced literally as laptops or palm tops or tablets. So this is something that it just shows the extent of hard work that has gone into creating such kind of machines, the extent of thinking that has come into development of such kind of devices. Anyone has come across this? It's like a vintage adder.
No, ma'am.
Okay. So I'll tell you, it's like a calculator that was used in previous times. So what you would do is, so the knobs that you see, dollars, times, and cents, so you would actually punch them, and so if you wanted to add 100 and then add 20, so first you would in dollars write 100 and then 20, so it would automatically add. So sometimes people who go for shopping, in previous times, they used to keep this with them, and as they would add items in their cart, they would also add the prices of individual items by punching all these three, and it would automatically add. So this is a very small demonstration of how addition as an operation was automated in previous times. So the beginnings, as I've already mentioned, before the 1920s, the computer denoted an occupation. Computers were people whose job was to calculate various equations, and many thousand computers were employed by government and businesses. So previously, computers were actually the people who were doing the computations, mainly related to solving certain kind of equations. Analog computers and first digital computers developed by the 20s and 30s were known as computing machines. But by the time it was 40s, computers were used interchangeably with computing machines. And analog computers relied on physical substances to perform calculations, such as turning of a shaft, because it was highly mechanical. while digital computers could process information and render a numeric value and store it as an individual digit. So what is the difference between an analog computer and digital computer? Yes, Sai Krishna.
Digital computer works on semiconductors, right? So 0 and 1, only two states, whereas analog can work in between those, like more than two.
So what is the system in the analog systems?
Gears.
Is it decimal? Is it unary? It's binary, or what is it?
In the digital, it's binary.
Okay.
And I don't know about analog.
Okay.
I know they work with gears, but I'm not sure.
Okay. So analog, I know, I'm not sure if in your BTech.
Analog uses mechanical devices, I think.
Okay. Analog generally talks about the continuous stream of signals. So moving forward, it was most people think in today's world that computer science means coding, programming in different languages, web development, and all kind of things. That is there, but it was actually like if you participate in ACM ICPC competition, which is mainly a programming competition, and when you really go and meet out people over there, you will see that because we start off through computer science by trying to understand how to solve a particular problem, how to develop a pseudo code and execute that code. Over the period of time, we start talking about things like complexity, the running time of the algorithm, and things like that. So mathematics is very closely related to computer science. It's actually mathematical logic that we are telling computer in a language that computer can understand. And that is what, now the computer can compute based on the mathematical logic that has been fed to that piece of machine. So with the rise in mathematics, the development in computer science saw the development it had never really seen before. So again, the name comes Alan Turing, and it's a very prominent name when it comes to computer science. So even though Charles Babbage laid the foundation of computing, it's Alan Turing who is regarded as the father of computer science, because he was the first one who could, in his 1950s paper, he talked about computing machines. So he provided a new concept of both algorithms and process of calculation with the invention of his machine. So I will show you a very short video, and then we'll start off. We'll put it off there. Okay, so let's watch this amazing explanation of Turing's machine. So is the screen visible, I hope?
Yes, ma'am.
Yes, ma'am.
Right, this guy is from University of Nottingham. He'll explain Turing machine. So, a very fascinating way in which he explains. Just listen to it.
Back at the start of the 20th century, mathematicians were fascinated by the question, just how much maths can we do? Not by using our gut feelings or intuitions, but just by following rules very, very carefully, by following an algorithm. In order to make that notion precise, we would have to set out just what do we mean by a program or algorithm. And this is where Alan Turing came in with his notion of a Turing machine. Turing was working on a problem in formal logic, and as part of his proof, he had to come up with a notion of any possible algorithm or any possible machine. He had to come up with a very general way of capturing how algorithms or programs or machines would work. This is where his notion of a Turing machine comes in. The way Turing described these machines goes like this. You have a way of writing down information in a coded form. His way was to think of a tape, which is as long as it needs to be. It's divided up into squares, and on each of these squares there's either a 1 or a 0, or we can have some spaces. Now what our machine does is it looks at the tape one square at a time. So you could imagine it as a little box running above the tape, maybe on little wheels, looking one square at a time. And that information codes up a question or a problem that we want solved. What the Turing machine does is really simple. At any moment in time, it's in a particular state, and it's looking at one square on the tape. And it has a logbook, a program book, and that tells it, if, for instance, you're in state number 23,
and you're looking at a 0, then rub out the 0, change it to a 1, move 1 square to the right, and move into state number 359, for instance. Or if you're in state number 359 and you're looking at a 1, leave that 1 as it is, move 1 square to the left, and move into state number 20. Really simple instructions. What the machine does is it starts off with a certain pattern of 1s and 0s. It follows these rules 1 square at a time, transforming that string of 1 and 0s into a different string of 1s and 0s. And eventually, hopefully, the machine moves into a halting state. It's finished, it's done. And what's left on the tape is the answer to our problem, coded up as 1s and 0s. That is such a simple process, but it turns out it's the essence of computation. Whatever any computer can do, it could in theory be done by that system looking at 1s and 0s on a tape. So that's why we say that Turing, in coming up with this idea of Turing machines, in effect came up with a blueprint for modern digital computers. Those computers manipulate strings of 1s and 0s to solve problems. This really simple idea that we find in Turing machines is actually so powerful that all modern computers basically do what Turing machines do. And we use this idea to evaluate the strength of modern computer programs. When a computer program can do what a Turing machine can do, we call it Turing complete. And that is the top of the hierarchy of program strength. So the strongest program that we can get does exactly what a Turing machine can do. We've never come up with a way of computing things that could do more than a Turing machine. So recently, there's been a challenge to the idea that anything a computer can do, a Turing machine can do. And the challenge comes from quantum computers, which almost seem like they can do things magically. My take on this is that a quantum computer can't do more than a Turing machine, but it can do things more efficiently. For instance, if you asked a classical computer to find you a phone number in the phone directory, you have to look through every single entry. It takes a long time. But a quantum computer can do that more efficiently. Don't ask me how.
So that was a short video on how Turing machine really works, and in my next lecture I will also give you a resource in which a particular person has actually developed a Turing machine using some hardware and software. So interested one of you can actually develop the Turing machine just for the fun of it. So hopefully in today's lecture you got a bit of understanding of the humble beginnings with which computers have started, and how we have come up to this time. In our future lectures, I will be discussing about we will be seeing a lot more prototypes of the computers that have been developed, and again with the chronology we will be understanding using different examples like ENIAC, EDSAC, EDVAC, and all these kind of machines that we will, and gradually coming down to the home computers. So that's all for today. Any questions?
No, ma'am.
Okay. All right. On that note, I will stop the lecture. I'm not sure what Adharv and Rachit are talking about.
Ma'am, is there any proof of that law in which we talk about in every 2 years the number of devices will increase?
Yes. In fact, that's my last slide in this lecture, in which I actually show you. I will show you right now. By law, don't think it of this as a law, a mathematical or thing. So it's more of an observation. Okay, it's more of an observation that says that this is how the processor speed has been growing. Okay, so that's why it's called as the Moore's law. It's
Ma'am,
more.
but now people are saying that Moore's law is dead. It doesn't work.
Yes, yes, absolutely. So there's a counter opinion that is coming up for Moore's law, and that's very interesting. I also recently talked about that. So what do you think it is failing? Why is the reason it's failing? What are the opinions and
Ma'am,
arguments?
now that sizes of transistors are literally they are atoms. They are shrinking to the size of atoms, so you can't shrink it further.
Physically impossible
More.
to go further down the
The
size.
laws of classical physics aren't obeying there, so that's
Okay.
why.
But the important thing to remember is that Moore's law was actually applicable for a certain period of time. And the fact that it no longer holds true in our modern times just tells us nothing very surprising. It just tells us, okay, things actually have always evolved. As new things evolve, there are always contradictions that are to the existing things. So, I mean, that is actually in the benefit of science and development. Okay. All right. So with that, I'll stop today's lecture. We'll meet on Wednesday. Carry forward our discussion on the history of computer science and understand. Yeah.
मैम फॉर्मेटिव असेसमेंट के लिए ग्रुप
Just a second. I think that is in innovation.